All right, let me start. Hi, I'm Ryan, and my project's about the difference between style GAN and progressive GANs. In this presentation, I'll quickly go through the background and the main ideas of the papers. Then I'll show you the details of my implementation. Finally, I'll share some results and my interpretation of them. So this is progressive GAN. The idea is to train gradually from low resolution to high resolution. And here's what part of the generator looks like. Each of these convolution blocks are for a specific resolution. Now, adaptive instance normalization, or ADA-in, is a way to align an image's look to the style of another. Here's an example of that. As you can see, aligning the content image to the style of this other image produces something like this. Same image, but with a distinct style. Now, Wasserstein GAN, or WGAN, is a technique that makes GANs easier to train. There are more details in this link. I'll just skim through this. So it's a different loss function that gives a linear gradients with some constraints, as opposed to like exponential. Now, StyleGAN is an improvement on the generator architecture of ProGAN. Through these fully connected layers, you get a better representation of the style of the image, which is then sent through these learned affine transformations and then applied through ADA-in at each resolution. The organic noise, like the details in the hair or the details in the grass, is abstracted out into this noise inputs. And this part focuses on the style, focuses on getting the style right, while this part handles all the organic variations. Now, the original paper has no visual comparison between the two, so I wanted to see it for myself. Especially, I wanted to see if StyleGAN adapts to new domains more efficiently. So this is my plan. First, I simplify both models. Then I train them to a comparable baseline. Finally, I try to transfer them to a new data set and see how they perform. Here are the simplifications I made. I reduced the resolution and the latent space dimension. I also reduced the number of convolution blocks. And what I end up with are these two models that have the same structure as the original, but at a fraction of the size, which makes it possible for me to train. Now, here are some snapshots from the base training. On the left is the ProGAN, on the right is the StyleGAN. Here are the samples of the baselines. All right, next, here we have the snapshots from the transfer learning. And here are the final results. On the left, we have ProGAN. On the right, we have StyleGAN. And here are some more results. Now, finally, so what have I learned? During the base training, StyleGAN takes longer because it's a more complicated model, but it seems to have a higher potential, meaning that better quality, even though it has better quality, even though it takes longer to train. And during transfer learning stage, StyleGAN is more stable. And somehow when I train ProGAN for too long, you get something like this. So yeah, I don't really know what's the cause of it, but that's what I get. And looking at the end results, you notice these bubbly artifacts here. These bubbly artifacts in the StyleGAN images. But overall, the good ones look a lot more fitting, and the details in the face is way more distinct compared to progressive GAN. So the facial details. Right. That's all. Thank you. Um,
So I should ask some questions now.
yeah, am I ahead on the schedule? Because I have my
I think it's
screen
fine.
share. All right.
Yeah, and normally you'd have 1 minute left for your presentation, but it's fine.
Sure. You
Now I can
start your
just ask
questions.
questions.
Yeah.
Yeah. So you mentioned that there are some bubbly artifacts when using Stalgan.
Yes.
And well, then why would you claim that Stalgan is more stable comparing to Progan?
It is more stable during in terms of the training. So the
Ah,
training loss is a lot more stable. The whole training process is a lot more stable. But in terms
okay.
of the output, you could say um, the program output is more consistent. Yeah.
Uh-huh. Yeah. Okay. Um, well, what do you think? Oh, so you all right then. So you don't know what caused the bubbly effects of the when of the outputs of the Stalgan, right?
I do have a hypothesis. I My hypothesis is that through morphing the latent space into a more disentangled and linear representation, so all the way here, through doing this, um, it kind of pushes all the nonlinearity into a much localized area. So even though most of the time it performs well, when you unfortunately like sample something from those nonlinear regions, you get these weird images. Well, that's
Uh-huh.
my guess, at
Okay.
least.
Uh, mm, so Stalgan in disentangles features, right?
Yes.
Well, is there a method for you to like get a view of what these features represent as an image?
To actually in the original paper to quantify the disentangledness and the linearity of the latent space, um, they proposed two new metrics called the perceptual path length and the linear separability, I believe. In terms of, yeah, so that's like how do you quantify those? But in terms of like visually how it is different, I think maybe by interpolating over specific parts of the Z space, which is the latent space, and checking the output can probably give a good representation. Yeah.
Okay. Yeah, I think that's it for my questions.
Right. Now I should stop the screen share, right?
Yes, should be. So
Huh.
wait for another 2 minutes.
Sure. Let me
All right.
figure out how do I stop share. Okay.
All right, I'll wait for another 2 minutes just to follow the schedule.
Sure. Jesus, there are a whole lot of people.
Yeah. Oh my God. Right. I'm Bruce, and today I'd like to introduce a new face hallucination technique with pulse. So face hallucination means to like generate high resolution images, especially on facial images from low resolution inputs. And the motivation of pulse would be previous super resolution methods. They often exist this type of blurring effect, some type of blurring effect due to the approach they use. And like for the most common approaches people used to use would be the LP norm of the super resolution image and the difference of the original high resolution image. And this often leads to an average effect of the pixels, which leads to the blurring effect. So Pulse set a new goal for the loss function. So instead of comparing the generated high resolution image with the original high resolution image, they now evaluate the difference between the original low resolution input and the generated image. So you generate a high resolution image and then you downscale it and you calculate the difference between the downscaled image and the original low resolution image. And by implementing Pulse, there are basically 3 steps. The first step is to find the face and downscale the region of the face to a 16 times 16 pixel image. And then in Pulse, it also applies StyleGAN just to for generating image. And the new goal would be like we search through the natural image manifold and you find pictures that downscales to this downscales to an image that is close enough to the original low resolution input. So and these are some outputs of applying Pulse. The first column would be the original picture, and the second column is the downscaled picture using bicubic. So this is this would be the input. This is the original picture. These are the inputs, and these are the outputs after like 200 stages of training. And this would be the process of the training of Pulse. Like this is the original picture, and this is after downscaling, and this would be the first image generated, and after some optimization of the proposed loss function, and this would be the output generated image. And as you can see that after downscaling, the low resolution image is kind of close to the original low resolution image, like for comparison. And like it shows that it is close, but I wouldn't say that it is like the same, and you can still see some difference between the original low resolution image and the generated low resolution image. And also like the second last picture here would be the 70th image generated, and the last input would be the 200th image generated. So I couldn't figure out why like there are like some more backgrounds and more, I would say more it would be sharper. The image would be sharper. Like I couldn't figure out what the reason of the difference from like 50 to 70 because it didn't change much, but somehow from 70 to actually it from 50 to 190 it all looks like these 3 pictures, but somehow from 190 to 200 it started adding up some features in the background. There isn't much take-home message, but I would like to stress that what the key of designing such model would be the loss function, because like the original loss function would be the something similar to MSE of calculating the MSE of the original picture and the generated picture, but you know that after generating a picture from a low resolution image, there are like infinitely many pictures you can generate, and it is just kind of unrealistic to actually pursue for the original high resolution input. So what would be better would be to like approach the input low resolution image, and it would be more realistic to like to apply. I wouldn't say apply, but to implement such a method. And this is another loss function from another paper, but I want to show us that you can what the key would be to like decide what loss function to use, and like there's an ID loss and like perceptual information loss. Like that would be the key for this implementing your goal. Yeah, thank you.
Okay. My first question would be, can you clarify on which part of this whole process is the pulse?
Okay, so the first align phase would not be part of the pulse because it was just like for generating your inputs, because the original input would be the high resolution input, a high resolution image, and align phase just it kind of catches the phase and downscale it. And but but for the second part, style GAN and applying the style GAN and optimizing the loss. Oh, I didn't mention it, but in the paper, it also adds some new constraints to the loss function. It not only optimizes this loss function, but also tries to like pushes the gradient to the surface of the manifold. And it is because of another bubble, a soap bubble effect, mentioning that the density is higher on the surface of the natural image manifold. And pulse would be, I would say that pulse is applying these two constraints and for
Okay.
optimizing the latent vector.
Okay. My second question is, are there any comparisons made between other competing upsampling methods in the paper?
Like pulse would be a rather old method, but it did compare with a PSP method, and the difference. This is the loss function for PSP, and like they both came out in the close time. So PSP actually is capable of doing super resolution, but PSP focuses more on maintaining the identity and other features. So Pulse is comparably
So
acceptable.
PSP is maybe more consistent,
Yeah,
but
PSP is
Pulse,
actually more a general model
oh,
that deals with different issues. Like you can solve super resolution or like face frontalization or in paint, like
oh,
in
I
paint
see.
something. Yeah, so uh Pulse would be like more focused on super resolution, while previous methods, there are other methods that are capable of doing other things rather than only super resolution.
Okay. Um, that's it.
Oh, sorry. Well, how did you? Oh, okay. Thanks.
Hey, Sean, I don't know if you're talking right now, but I don't think we can hear you through your mic.
Yeah, I cannot hear anything either.
Oh, sorry. Can you hear me now?
Yeah.
Okay.
Yep.
Sorry, my microphone had an issue. Okay, I'll go through this briefly. So my topic is self-supervised image denoising, and it's based on the paper Noise to Self. And basically, we would like to do image denoising. And the existing denoising methods, they all primarily rely on clean reference for training. And however, in real life scenarios, it is often difficult or expensive to obtain a clean image. So how do we denoise in a self-supervised manner? A prior work to this is noise to noise, and basically it used another noisy measurement as a label. And it turns out if you train a model on that, you'll just get the same result as using clean labels. So self-supervising is all about using the noisy input itself as a label. And we look at the loss function here. If we try to minimize this, we'll only learn the identity. So we have to cripple the function f in some way in order to prevent this from happening. And how the paper do this is they propose an idea of J-invariant function, which, to be a J-invariant function, the function has to use information from outside of each subset of dimension J to predict the value insides of the J. Basically, it has to use any other information other than itself in order to predict the value for itself, like the picture shown here. And another proposition is that the self-supervised loss is equal to the ground truth loss plus the noise variance for any J-invariant function. And this is a good proposition because now we have an actual way to compare the performance for a J-invariant function compared to if we have a ground truth loss. So the first implementation is the donut median filter. Basically, we remove the center part of a median filter to create a donut filter. And this acts as a naive J-invariant function because now, in order to predict the value for the center pixel, it no longer can take the original information from itself. And you can see from the graph here, there is a constant of difference between them, just as the previous proposition mentioned. Next, we calibrate a wavelet filter. Basically, we use this function here. We calibrate the original wavelet filter into a J-invariant version 1. So we can do self-supervised denoising in the same matter. And from the graph here, you can tell it has the same results. Next up, we do this on a self-supervised neural network. We train a J-invariant version of the neural network by replacing grids of pixels with the average of their neighbors. And then we only evaluate the models on these masked pixels in order to achieve a J-invariant function. And we use MNet dataset and DNCN model. And here are the outcomes of it with using different kinds of masks. Lastly, we implement a single-shot self-supervised denoiser, which is our original target. And the training process is similar to the previous one. However, this time the only input is the single noisy image, hence the name single shot. And we compare it to performance, other benchmarks, denoising performance, other benchmarks, denoising methods like BM3D and non-local means. And it turns out that it can achieve the same level of denoising with similar PSNR value. So the take-home message here is you can consider J-invariant functions as a trade-off between information and optimal calibration, because you lost some information, but you can gain actual ideal denoising outcome. And how to choose an optimal J-invariant function for a specific signal are still an open questions. Lastly, this framework is feasible and achieves the similar performance with other supervised ones. Again, that's it. And I think my discussion is supposed to ask a question.
Can you hear me?
Yeah.
Okay, so my first question is, what is the purpose of the donut filter, especially when a regular convolution filter seems to maintain a consistent offset from the ground truth?
Okay. So the donut filter here basically acts as a naive J-invariant function, and just to show, that the proposition we made before are true. So here, you can see the blue line here, and the dotted blue line here. They actually have a constant of difference between them. In comparison, if you looked at the orange line, which is the original median filter, which is not a J-invariant function, there is no consistency between the two orange lines. Yeah, so basically the donut filter here is just to act as an example.
Okay.
Mhm.
My second question is,
Yeah, I think my time is up. Yeah, I'm very
Okay,
sorry
sure.
about that. Yeah. Okay, I'll stop sharing.
okay, it's my turn now. Okay, so my project is named Navigating the GAN Latent Space for Desired Image Transformation. So basically what I'm doing is I try to manipulate the latent vector to achieve desired image transformation. So the diffusion model is proved to be more powerful nowadays, but GAN is more computationally efficient than the diffusion model. However, GAN is unpredictable, so I try to gain some control over GAN. So what is latent space manipulation? In this graph, you can see Z is a data point in latent space, and you manipulate it to another data point, and resulting in the image space for a desired image transformation. So the paper proposed three methods. This first method is called a linear walk. So basically, it just add in vector omega times the scalar alpha to the original data point to achieve the desired image transformation. And this is its loss function. So in this picture, you can see when alpha equals 0, that means the data point in the middle. And by adding omega, you can see the phase get zoom in. And the second method is called a nonlinear walk. So instead of directly add a vector to the original data point, use a nonlinear transformation function to transform the original data point to achieve the desired image transformation. So in this picture, you can see the face is gradually shifted to the right. So the previous slides assume a fixed pre-trained generator, but model have its limitation. So if your GAN is trained on a biased dataset, it cannot produce some desired transformation. For example, if your dataset only consists of male faces and you ask it to transform a male face to a female face, it does not know what a female face look like. So the message street is jointly optimized the GAN with the walk function. However, it's very computationally heavy. So for this project, I re-implement the first two methods using style GAN 3 as my GAN and use this generator as my pre-trained generator and train it on another data set, which mainly consists of Korean faces. And for method 3, I use MNIST dataset on a DCGAN. So I also conduct several experiments. So for the first two methods, I swap the generator. So basically, I learn a linear walk function from generator A and then test it on generator B, see if that work. And for the third method, I just compare it with a fixed generator. So the results are successful. Generator swap experiment works, but the entanglement is very severe. So you can see the face get gradually zoom in or rotate or shifted to the right. And so does the linear walk function. And for the generator swap experiment, you can see that a walk function learned from generating Korean girls' faces also can perform the desired image transformation on the original FFHQ GAN. And this is the result of the third method. So you can see when using a fixed generator, the generator does not know what a rotated 7 looks like. So the 7 just stay the same. However, if I jointly optimize the generator with the walk function, now the generator know what a rotated 7 looks like, but the quality decrease. So here's some take-home message. So jointly train the GAN with walk function is more computationally heavy, but has better result. And latent space entanglement is still an issue. So here you can see, although the face is gradually rotated, it turns into another person. So here's some future direction. So we might use identity loss to reduce entanglement and explore additional technique to enhance control and diversity in latent space manipulation. Okay.
Okay, so I'm going to ask some questions now.
Sure.
Okay, yeah, so for this slide, what does identity loss mean?
Oh, so in this paper, how they measure the difference between generated picture with the desired image is they use L2 norm to measure the difference between the generated picture and the desired picture. However, identity loss is identity loss measure use a more complicated technique to measure the difference between two pictures, so that this you can see clearly this person and this person does not look the same, so their identity loss will be bigger.
Oh,
Hello?
so okay, so
Okay.
basically, so like instead of like pixel to pixel L2 norm, it used another like a more advanced criteria to calculate the loss.
Uh,
Is that it?
yeah, right.
Okay. Another question is like what exactly does entanglement means here?
Oh, so okay, in this picture you can see, although the face gets zoomed in, however, this bald guy turns into another guy with a glasses.
Glasses?
Yep. So entanglement means that several feature
Is also
entangled.
getting changed together,
Yeah.
right? Ah, okay, I see. Hmm.
Okay.
Yeah. Can you go to it? Okay.
Right.
Wait, is that it?
Do you have another question?
No, I'm fine. Thank you.
Okay. Okay.
I think my mic is working, and I think you can see my presentation. Just let me know.
Yeah.
Yep.
Okay, perfect. All right. My name is Aiden Goen, and my paper and my implementation is an expansion of plan and solve prompting. Let me first initially talk about plan and solve prompting, as it is like a diversion from prompt engineering. And prompt engineering is the study of like designing inputs for generative AI and large language models to produce optimal output. In this case, like the very basic level of prompt engineering is zero-shot prompt engineering and few-shot prompt engineering. In this case, it's like zero shot, for example, is you're just asking the large language model a question, and you're basically just telling it how you want it to answer that question without giving it examples. So I mean, there's some examples down here within this image that kind of give way of like zero shot. And then if you look over here to the model input on the right, for that's few shot prompting, which is the same thing where you're asking it to answer a certain question in a certain way, but you also give it examples of how to answer that question before you actually ask the large language model to answer that question. So the paper I reviewed implemented a new version of prompt engineering, or their own like little diversion of prompt engineering called plan and solve prompting. Plan and solve prompting basically just takes like very complex questions that usually large language models aren't able to answer, and asks it to devise a plan and carry out subtasks of answering that question, so that it can actually like create a plan on its own and like create variables depending on if the question needs math or not. Basically, just trying to put more complex human thought within the large language models to hopefully produce better output, and be more efficient and effective in answering more complex questions that it's been asked. The results, they did the plan and solve prompting across 3 different types of data sets. There's common sense data sets, there's math data sets, and there's symbolic data sets. They compared their plan and solve to like chain of thought prompting, which is basically like a widely reviewed prompt engineering technique, which asks the AI or the large language model to create a chain of thought in its engineering. As you can see, plan and solve, like in this zero shot output, where you're not giving examples, outperforms chain of thought in almost every single instance, but it has comparable or worse performance when compared with few shot chain of thought. So this is kind of the motivation for my for my project and for my implementation. Although like plan and solve plus, and the difference between plan and solve plus is that plan and solve prompting is like a general for any type of question, and plan and solve plus prompting was plain and salt, like prompts given based on the types of data sets. So they're more specified and usually perform better than basic plain and salt prompting. But like I said, because of like the worst performance compared to few shot chain of thought, I wanted to try and implement plan and solve plus prompting with few shot by also giving examples on how to answer in the plan and solve methods while also giving it the prompt. Like I said, I wanted to implement few shot plan and solve plus, and to get the examples, I took three different domains of data sets: the math data, one of the math data sets, which is GMS 8K, one of the common sense data sets, which is common sense QA, and one of the symbolic data sets, which is last letter. Basically, last letter is it's just giving the large language model 4 words, and it wants to take the last letter of all those words and concatenate them into one string. Whereas like common sense QA is basically just common sense questions, and GMS 8K is pretty complex math questions. And what I did is I took some examples from the generated results of the paper and where that the plan and solve actually got them incorrect. And I would update these to have the AI do the plan and solve in a correct way, and then added that as examples within like the few shots, or within the few shot plan and solve prompts that I was giving it. And also, these data sets are rarely pretty large, but I only use 100 samples with each data set, as I had to use an OpenAI key. That would have taken a lot of time, and also taken a lot of expenses, as you have to pay to use OpenAI API keys. As you can see, these are the results I had. For the few shot plan and solve plus, they perform almost exactly like the 0 shot plan and solve plus, with the 59%, and few shot plan and solve plus actually doing worse. And they do significantly worse in the common sense data set, which was an interesting result. As you can see, it's 74% for 0 shot plan and solve plus, and 68% for few shot plan and solve, and 66% for few shot plan and solve plus. But within the symbolic reasoning data set, the last letter actually outperforms it by a great margin, both being 89% for the few shot and only 81% for the 0 shot plan and solve plus. The results did not fit my original hypothesis that combining few shot with plan and solve prompting would actually increase the accuracy of large language models across these complex data sets, except for with the last letter one. It comes with a lot of reasonings. Sometimes for large language models, too much context can confuse it, especially with complex data sets where each question is worded very differently, and giving it examples, giving only like a couple of examples of answering it in a certain way, it's going to make the large language model only think in that method whenever it solves all the other problems, even though all the other problems need to be solved in different methods. Whereas last letter is pretty much you answer the same way every single time, as you're just going to concatenate the last letter of 4 words throughout the entire data set. So that's why it saw a great increase in accuracy. So that's why sometimes 0 shot prompting is more effective than few shot, depending on the types of data sets that you're using. Yeah, and that's my entire presentation.
Hi, Aiden. I had a couple of questions.
Okay.
Yeah, so to be clear at first, you use those techniques on the available large language models, right?
Yeah, I which models?
Large language models. You use those techniques on the large language models that are available, publicly available, like ChatGPT, right?
Yeah,
Is
yeah.
that how
So
you did?
yeah, that's what within my like actual implementation, I did ChatGPT 3 because that's what the original paper did. But it also allows it to do like chat. You can also take this like information and also do it across different other large language models like ChatGPT 2 or 3.5, or also ChatGPT 4. I just did it across ChatGPT 3 because I wanted it just to be able to compare to the original paper's results.
Yeah, right. My next question is on that. Actually, since I was curious about how the output would change if it was done in the other kind of models, because maybe one of the methods that perform well on ChatGPT may not perform that well on the other model, right? Did you try that? Something like
Yeah,
that?
I didn't have enough time to really try that. That was definitely going to be in my implementation at first, but then I had to switch one of my implementations. But I think it would definitely improve within ChatGPT 3.5 Turbo, because 3.5 Turbo has more updated like data sets for it, and it's also much faster than ChatGPT 4, and would have actually been more efficient than ChatGPT 3 also. Yeah, I originally planned to also test it across ChatGPT 3.5, but I just didn't have time to get there.
Yes. Also, you compared the results with chain of thought method, right? In the results part, I think. Yeah, I was interested in knowing about if there are other such techniques that that exist, and which are the best ones that you have come across while doing this project. So it would
Yeah.
be, yeah.
Yeah, definitely. So there's, I mean, two other papers that I reviewed within like all the three papers that we had to review for the project. Two other ones were also went across, like explored other forms of prompt engineering techniques, and one in particular known as Tree of Thoughts is like getting pretty popular right now, where it basically asks the AI model to like create a tree of thoughts, and like that way it can the tree of thoughts, it's kind of hard to explain without like a visual, but it's probably the more popular one right now because it allows the large language model to go back on its answers rather than just like keep on going with the variables that it has. It'll like create some variables and some tasks, complete those tasks, and then it'll review its tasks. And if it sees an error and whatever it did wrong, it'll go back and actually restart. So yeah, I reviewed a paper along that, which also used some of the data sets within here and actually performed better than the plan and solve prompting. But I just originally wanted to do this implementation to compare zero shot plan and solve versus few shot, obviously.
Thank you. That was interesting. So
All
thank
right.
you for the presentation.
Yeah, thank you.